Hello guys, how are you? Our video today we're going to talk about half-life and half-life calculations. First of all, what is the meaning of half-life? As you can see at the screen, half-life is the time needed for one half of an amount of a radioactive nuclei to decay, which means how long we need to make half of the initial quantity disappear. And this is something natural. So for example, if we look below here, we can see this table, the half-life of some elements. If we look at carbon 14 isotope, we can see that half-life is 5,715 years, which means that if we have 10 grams of carbon 14, after 5,715 years, we will have from this 10 grams, we'll have only 5 grams because half of the quantity will be disappeared and decays. And after another 5,700 grams, half of the new quantity, which is 5 grams, will be also disappeared. So we will have 2.5 grams, and so on. So half-life is the period of time required for half the atoms of a radioactive nuclide to decay or disappear. Now, as you can see here on this table, some elements or some nuclide half-life is very, very small. Like for example, if we look at polonium 214, the half-life of it is 163.7 microsecond, which means it will decay very fast. It's not stable at all. While polonium 218 isotope need 3 minutes to decay. While other elements like for example uranium 238 isotope has a very, very large half-life, as you can see. So we can say that this is a totally non-radioactive element. It will never be disappeared. We are talking about billions of years. Now, we're going to see some examples, the calculations related to the half-life. In this example, as you can see, phosphorus 32 has a half-life of 14.3 days. How many milligrams of phosphorus 32 remains after 57.2 days if you start with 4 milligrams? So here we have the total period is 57.2 days and half-life is 14.3. Simply by dividing the total time over the half-life, we can see how many half-life periods we are talking about, which is here, if we divide 57.2 over 14.3, you will have 4 half-lives. So 4 half-lives means that at the first half-life, we will have 2 milligram. Second half-life, we will have 1 milligram. Third half-life, we will have 0.5 milligram. And at the last one, we will have 0.25. Or, as you can see here, we start with 4 gram or milligram, whatever. At the first half-life, only half of this quantity will be disappeared, so we'll have 2 gram. At the second one, half of the 2 is 1. At the third one, half of the 1 is 0.5. And at the last one, which is the fourth one, we have 0.25 gram remains. Another example here, let's talk about this example here. The half-life of polonium 210 is 138.4. So half-life is 138.4. How many milligrams of polonium remain after 415.2 days? So 415.2 days after. If you start with 2 milligram of this isotopes, so the initial quantity is 2 milligram. First, we have to find how many half-life periods we have. So simply 4.15.2 over 138.4, which will give us 3. So we are talking about 3 periods of half-life. So with 2 milligram, at the first one we will have 1, the second half-life we will have 0.5, and at the third one we will have 0.25 milligram. Or we can use a formula which is NT equal N node times half to the power T over half-life, where NT is the total quantity, N node or the final one, N node is initial quantity, T total time, and T half is the half life. This is the equation or the formula that we can use to make our calculations. If we applied this formula at our previous question, as you can see here, the half-life, which is T half, is 138.4. So 138.4. The total time is 415.2. 415.2. And the initial quantity is 2 milligram. So what will be NT? Simply, you can see NT equals N node, which is 2, times half to the power total time 415.2 over the half-life 138.4, which will give us NT equal 2 times half to the power 3, which means 2 times 1 over 8, which equals 2 over 8, which is 1/4 over 4, which is 0.25. Same answer. Now let's go to solve another question. Assuming a half-life of 1599, so T half equal 1599 years. How many years will be needed for the decay of 15 over 16? So decay of 15 over 16 of the initial period, of the initial quantity, sorry, of a given amount of a radium 226. Means how many years we need to decaying of 15 over 16 of the initial quantity for this isotope, if the half-life is 1599. First of all, we are talking about decaying of 15 over 16, which means that we will still have 1 over 16 after this quantity. So this is in total. And in node or in initial is 1. As you can see here, we need in total and in node. So simply in total equal in node half to the power time over half-life. So the total quantity left is 1 over 16 equals 1 to the power half over the time is unknown over 1599. So first of all, we need to find the power. Assume this is x. So we will have 1 over 16 equal 1 times to the power x, which means 1 over 16 equals half to the power x. In this case, x must be equals to what? 4, because half times half times half times half equal 1 over 16. So x must be equal to 4. So we just go back to x, so which is t over 1599 equals 4, which means t equals 4 times 1599, which is you can use calculator. Years. So this is the period of time needed to still have 1 over 16 or to decaying of 15 over 16 of the initial quantity. We have here another questions. Question number 3, 4, 5 in your textbook, page 649, and I hope that you are going to solve it. The second point we are going to talk about here is that sometimes we could have a decay series that could happen for the radioactive nuclide to be stable. And in this situation, we will have like a series of equations and decaying steps. The isotope will be decayed to another isotope, and this new one will not be stable, so it will decay again and again and again to reach finally the most stable isotope. In this scenario, as you know, we will start with the first arrow, which we called it parent nuclide. So the arrow or the nuclide that will be at the top of the series will be called parent nuclide. And all of the other nuclides that are produced by this decay is called daughter nuclide. And all naturally occurring nuclide with atomic number greater than 83 are radioactive. So usually we can consider all nuclides with atomic number more than 83. We are talking here about elements after lead, because the atomic number for lead is 82. After that, we can consider them radioactive elements and belong to one of three natural decay series. Nuclides are uranium 238, uranium 235, and thorium 232. So, as a start, the transmutation of uranium 238 decay series are charted below. And as you can see in this equation, it will be a transmutation to change uranium to thorium with emission of alpha particles, which is helium as we see here. So this is the series, uranium decay series, as you can see. The uranium here is the parent nuclide. The first one is parent nuclide. Now, why we have some blue arrows and red arrows? As you can see here, the blue arrows reflect alpha emission, while red one shows or represent beta emission. So we have to know here that when uranium converted to thorium, this process will include what? Emission of alpha particles or helium 2, 4. Then thorium goes to transmutation to palladium and uranium, two steps together, with emission of beta particles. So emission of electrons. And if you notice here, when uranium changed to thorium, the atomic number decreases by 2 and the atomic mass decreases by 4, because helium atomic number is 2 and atomic mass is 4. While when thorium changed to palladium and uranium, as you can see, the atomic number increases, because this is emission of beta particles, and we said that beta particles are electrons. So the neutrons here will be converted to proton and release the negative charge, which is electron. So the atomic number will be increases and the atomic mass will stay the same. So remember our previous lesson. This chain continue to form many and a lot of daughter nuclide. Finally, we will reach the lead at the last one, which is very stable element, 206 with atomic number of 82. Now, sometimes we could have a possible transmutation with the dotted arrows like you see here. This means that possibly the atom here will be converted to another atom. So we are talking about possibilities. This is everything for our lesson today. and I hope to see you in our next lesson when we're going to talk about how we can make nuclides radioactive artificially. Thank you and have a nice time.